Older style cooling systems rely on relays for switching individual fans on or off. However, this can get confusing when multiple relays are used for variable speed activation. OEMs may use different fan configurations depending on the size of the engine. A small capacity engine may use a single fan with 2 speeds, whereas a large engine may utilise dual fans with multiple speeds. A single fan will normally comprise of a 12-volt motor with the internals consisting of either 2 or 4 brushes and the corresponding number of permanent magnets. A fan speed resistor may also be used to alter the fan's RPM. Some OEMs may use 2 fan motors operating at 1 speed. This enables the same airflow as a single larger fan but takes up minimal space. A cooling system that incorporates 2 cooling fans that operate at different speeds will use electric motors with different operating wattage outputs or dissimilar fan blade diameters. Suppression diodes may be installed in the fan's motor, module or relays. When not in use, they eliminate any generated voltage from the fan motor when turned by the incoming airflow. If these diodes aren't used, the generated voltage may affect the correct operation of the relays or even spike the ECM. A system using 2 normally open relays can be wired in series or parallel to achieve low or high speed operation. If relays aren't your forte or you just need a quick refresh, please watch our in-depth module on automotive relays. Looking at this schematic, battery voltage is supplied to terminal 30 with ignition voltage supplied to terminal 85 of both high and low speed fan relays. Low side drivers within the ECM are used for control of the low and high speed fan relays. Using data from the ignition, air conditioning switch position, engine speed and coolant temperature, the ECM will refer to its cooling map and will ground either the low speed or high speed fan driver to achieve the desired level of cooling required. The low speed fan will engage when the coolant reaches a predefined temperature or when the air conditioning is switched on. Operation of the low side driver completes the ground circuit for terminal 86. Battery current now flows from terminal 30 through to terminal 87. A fan speed resistor connected in series causes the motor to turn at a lower RPM due to the reduced current flow. As engine load and coolant temperature increase, the ECM will look to the cooling map to see whether the high speed fan is now needed. The low speed driver turns off and the high speed driver turns on, completing the ground circuit for the high speed relay. Battery current now flows to terminal 87 and bypasses the fan speed resistor, allowing the motor to operate at a higher RPM. The high speed driver is commanded off once the coolant temperature has dropped to a predefined value. This opens the high speed relay contacts, removing current flow from the circuit. By using 3 relays, we can now control dual motors to achieve low, mid and high speed operation, eliminating the need for a fan speed resistor. Looking at this circuit, we have 2 normally open relays and a 5-terminal, normally closed or changeover relay. Voltage is supplied to the relays via the battery and ignition feed. The circuit is complete when the ECM controls only one or a combination of the low side drivers. When the low speed fan is required, the motors are connected in series, causing a voltage drop which reduces both motors' RPM. Only some OEMs use this type of mid-speed operation. When high speed is required, the fans will operate in parallel. Each fan has their own dedicated circuit, allowing for maximum current flow through both motors. For the low speed fans to operate, the coolant must reach a predetermined temperature or the air conditioning is switched on. The ECM will then ground the low speed driver of fan relay 1. This completes relay 1's control circuit, closing the normally open contacts, allowing current to flow to the right side cooling fan. The current will flow to terminal 30 of relay 2, and then 87A, continuing to the left side cooling fan and then ground. As the low speed fans are now connected in series, the total circuit resistance will increase, causing the motors to turn at a lower RPM. Again, in this instance, mid-speed operation is achieved using the larger fan. The ECM grounds a separate driver, completing the control circuit for relay 3. Relay 2 has no effect on the circuit at this time. Battery current flows through relay 3 to the left cooling fan where it is then grounded. The operation of the single large fan creates more airflow than the dual fan low speed function. The high speed fan will be engaged when the coolant temperature reaches a predetermined upper limit. The ECM now grounds both drivers simultaneously. Relay 1, 2 and 3 control circuits are now completed with their load contacts closed. Battery current flows through relay 1 to the right side cooling fan with the ground circuit now supplied through terminals 30 and 87 of relay 2. The left engine cooling fan receives current from the still closed relay 3 and is grounded to chassis. Both cooling fans are now connected in parallel, reducing the total circuit resistance. This allows maximum current flow through both motors. This next system uses one cooling fan, a combination of relays, resistors and ECM control to achieve 3 different speeds. At low coolant temperature and with the air conditioning switched on, the engine control module will ground the low speed driver, completing the control circuit for relay 1. Relay 1's load contacts close, supplying a ground circuit to the control side of relay 2. This closes the low contacts of relay 2, allowing current to flow from the ignition supply through relay 2 onto fan speed resistor 1. This resistor reduces current flow to the fan motor, causing it to turn at a low RPM. Even though relay 3's load contacts close, it has no effect on the circuit. For the mid-speed operation to engage, the ECM grounds a separate driver, completing relay 4's control circuit. As the load contacts close, ignition current flows through relay 4 to fan speed resistor 2. Resistor 2 has a lower resistance than resistor 1. This results in a higher RPM output from the motor. Again, even though other relays receive a ground from the ECM, this will have no effect on the mid-speed operation. For the high-speed fan to engage, both drivers are pulled to ground within the ECM. Relay 1 control circuit is completed, closing the load contacts, allowing a ground path to relay 3 control circuit. Relay 3 load contacts are now closed, allowing ignition current to flow to terminal 86 of relay 5. Relay 5's control circuit is now complete, causing its load contacts to close. Battery current now flows through relay 5 to the fan motor, bypassing all resistors. This allows the motor to operate at full RPM or high speed. Again, even though other relays are engaged during high-speed operation, they have no bearing on the high-speed circuit. Understanding the how and why behind the operation of cooling fans and their electrical circuits will ensure the correct diagnosis is performed every time. Thanks for watching. See you soon.